Okay, I'm going to talk about circular motion, also known as centripetal motion. Centripetal means center seeking. Don't get this confused with the word centrifugal with an F, which is not a real thing. Centripetal motion is center seeking. So I have a picture here of the Earth circling the Sun. And there's a couple things I want to point out. The Earth circles the Sun because there's a gravitational force on the Earth due to the Sun, and I express that as an arrow right here. That would be the force of gravity. Now, the Earth pulls on the Sun with the same amount of force, but because the Sun is much more massive, it has a much smaller acceleration. Today, we're just going to worry about the Earth. And so the Earth goes in what is a mostly circular path around the Sun. It's important to keep in mind that this force is towards the center. F sub c is the centripetal force, is towards the center. And because the force is towards the center, the acceleration is also towards the center. So if we orbit the Earth 90 degrees around this, we have a centripetal force and an acceleration that is towards the center of the circle, aka the Sun. The same is true here. Force and acceleration are towards the center. I left a space in here though because I want to point out that F sub c is not a real force. There is no force out there called a centripetal force. In this case, there's a gravitational force. And it's that gravitational force that creates this thing that we might call F sub c, that centripetal force. It's really gravity that's pulling it in. Just like there's not a net force. And in fact, if you look at this, you'll see that there's only one force acting on the Earth, and that is the force due to the Sun, the gravitational force. So F sub c is not only not a real force, just like F net is not a real force, F sub c is equal to your net force, neither of which are real, both of which are created by gravity. And because it is, it's equal to mass times the acceleration. So you ask yourself, hey, this thing could be moving at a constant speed, right? So why does it have a force or an acceleration at all? Well, it's constant speed, but the direction of motion is changing. And since acceleration is a change in velocity, and velocity is not just speed, but direction. If the velocity vector direction is changing, you have an acceleration, and thus a net force. Now, the question is, what keeps the Sun from sucking in the Earth, right? We have a force on us towards the Sun. Why doesn't the Earth fall into the Sun? Well, let's look at the path of the Earth right here, here, and here. I've drawn in blue velocity vectors. V is the velocity. And we can see that at these three different paths, the velocity direction changes. So what happens is that acceleration might not be changing the speed, but it's being used to change the direction of the velocity. So if the Sun were to totally magically disappear, the Earth would just keep going off in this direction forever and ever and ever. But because the Sun is there, Newton's first law, right? An object stays in motion in the same direction unless there's an unbalanced or a net force. Because of an unbalanced or net force, the velocity changes, causing the direction to change, creating that centripetal motion. Now, last thing that we need to get to is some of the mathematical stuff, looking at your acceleration. So the acceleration is equal to v squared over r. And I could graph it like a versus v is going to look exponential, a versus r is going to look inverse, etc., etc. But ultimately, your acceleration is velocity squared over radius. Now, your centripetal force, as we said, is equal to net force. And net force is just mass times acceleration. So this will be m times v squared over r. And sometimes you'll see questions that say, what happens to acceleration and force if you double the velocity? Well, if you double v on the right side, you're making the right side bigger, you got to make the left side bigger, right? So if v is doubled, and that's squared, that's 4 times bigger, so acceleration's got to be 4 times bigger, assuming you keep the radius constant. The same is true with this. You double v, v is squared, that's 4 times bigger, so this has got to be 4 times bigger. What happens if you double the mass? Well, with force, you double the mass, you double the force. Here, there is no mass, so doubling the mass has no effect on acceleration whatsoever. So this is an introduction to centripetal motion. This is just a kind of simple 2-dimensional introduction. You can get into more complex 3-dimensional motion. Just keep in mind that net force is the same as centripetal force, and it's caused by something else. So maybe I'm spinning something in a circle, and if I'm spinning in a circle, it could be a string or a tension force that is creating that centripetal motion. And sometimes you might need to find velocity based on how long does it take to go around a path, for example, of radius r. So if you want to find the velocity, you can say, hey, it's distance divided by time, right? If it's a constant speed, it's just distance divided by time. And distance is the circumference, which is 2 pi r divided by the time. So you might end up using that as well if you figure out if you know the radius and you need to find the velocity, you can use it through that. Okay, I think that's it. Thank you very much for watching.